Okay. So, good evening, everyone. I am Avik. I'm a PhD research scholar at the Department of Electrical Engineering at IIT Madras. And today I welcome you to the sixth live session for Introduction to Wireless and Cellular Communications. And in the sixth week, you were introduced to the one of the most fundamental concepts of wireless communication, which was the wide sense stationary uncorrelated scattering model, or WSSUS model for short. And we saw a lot of different aspects. We studied the channel response in rigorous detail. So the channel response, if you recall, was denoted by h of two parameters. It's a function of two parameters, namely t and tau. So t is the time dimension and tau is the delay dimension. So we saw that whenever we are referring to variation of time dimension, we are dealing with the temporal characteristics of fading channels, and variation of tau means time dispersive channel. And we looked into the other aspects, some of the quantities like level crossing rate denoted by n suffix v, then average duration of fade, all those parameters we studied. We looked at their expressions, mathematical expressions, and in the end we also looked into the classification of different fading channels. So depending on the okay, let me admit. So as I was saying, in the end we also looked into the classification of fading channels. So depending on the situation, there can be different types of channels, such as the slow fading or fast fading, flat frequency flat channel, frequency selective channels, and so on. So if you recall, there was a plot in which there were 4 different quadrants which corresponded to 4 different situations and different types of channels. So with all those things in mind, let's begin with our today's session. And and also I think it's a good idea to show this before actually we begin our session. So in the last class, I think some students were asking regarding the exam and all. So if you want to know about the details of final exam, so you can straight away visit the NPTEL course webpage, so which is this, right? Introduction to Wireless and Cellular Communications. And if you scroll down, you will find all the details here about the course. And if you scroll down in the bottom, see the date and time of exam is mentioned clearly. It's 29th October. Yeah, there are 2 sessions, morning and afternoon sessions, and the criteria to get a certificate is given clearly, and what are the marks requirements and all has been given here, right? And so you can go through this. So there might be okay, I think someone wants to join. So the number of questions must be quite a significant number, but it doesn't necessarily imply that all the questions will be lengthy. So the standard might be a bit difficult as compared to the assignments, which is naturally obvious, but the pattern would be the similar. So to the best of my knowledge, I think it's a 3-hour exam, and it will comprise of 2 sections, section 1 and section 2. and the full marks is 100, and the first section consists of 20 questions of 1 mark each, and the second section consists of 40 questions of 2 marks each. So total you have 20 plus 80, which is 100 marks. Okay, and 3 hours would be the time. So yeah, but yeah, this is just a tentative information that I have, and for the rest of the things, certificate and all marks things I just showed you, you can refer to the course web page. Everything is mentioned. Okay, so let us begin. Okay, so okay, I think someone has posted something in the chat. Okay, I think I heard someone posting something in the chat, but unfortunately I am unable to see anything. Whoever, if someone wants to post anything in the chat, I would prefer if you can just unmute and speak. By the way, I expect you can see my screen and all, right? And I'm completely audible and all. Okay. I think this seems to be some issue with my chat box, or I don't know. I can't look at the chats. I mean, it's completely blank to me. So please, again I'm saying, please just unmute and speak. Okay. All right, so let's look at the first question. I keep hearing the chat noise for some reason. I'm not sure. Let me just rejoin. Okay, let me rejoin. I don't know what's happening. Okay, let me share my screen again. Okay, so hopefully you can see question number 1 on the screen. Please read the question. Okay, I keep hearing that the chat sound. I don't know why this is happening, but anyways, again please unmute and speak if you have any queries or anything. So let's look at the first question. So the probability of error in AWGN is given. Okay, it's very difficult this way. How do I get rid of this annoying noise? Okay, let's see. Maybe now it seems oh my god, it's happening again. Are others also hearing the same sound, that notification sound? I don't know if it's only me, or if anyone has any solution to this, please feel free to help me out, because it's creating a lot of disturbance. Anyways, let's continue. So please read the first question, everyone. So the probability of error in AWGN for a particular modulation scheme is given. That's the expression, and this is the expression in terms of the instantaneous SNR. Oh, okay, why this is happening? So 4 times e power minus gamma, that's the bit error rate for AWGN, where gamma is your instantaneous signal to noise ratio, and we are asked to find the probability of error in Rayleigh fading with average SNR, which is capital gamma, given to be 16 dB. So what will be the probability of error in fading, Rayleigh fading? Okay, so this kind of questions has been discussed in the lectures also before. In fact, I think in the previous weeks only, the actual process of deriving the probability error for fading, given the probability of error for the AWGN. All you need is the distribution as the additional information, and you just integrate the product. Yeah. So let's first look at the general process, how we solve it, and then if you recall in the lecture number 24, I guess, of week 6, there was a shortcut also. So there was a trick. If the probability of error takes a particular form, then we can straight away write the expression for the probability of error in fading. Okay, so we are looking at question number 1, and so first let's look at the usual method. Okay, this is, let me first try without the earphone if it's still. So are people able to hear me?
Yes, sir.
Okay, but this sound is still, I don't know, still coming. I don't know what's the issue. So it made no difference. So my apologies for this, but I don't know the exact cause behind this. We will try to continue within this only. So yeah, and thanks for responding by unmuting. So please do it for today at least. Okay. Okay. All right. So the question we have discussed, right? So given, first we will look at the usual method. So the probability of error in AWGN for any particular modulation type is given to be 4 times e power minus gamma, where gamma is your, this is small gamma, instantaneous SNR, and capital gamma is the notation for your average SNR, okay, which is expectation of your small instantaneous SNR, right? Average means the expectation. So in the problem you are given that the average SNR is 16 dB. Okay, if you look at the question, it's 16 dB, and the first basic usual step is to convert these SNR values from dB scale to your linear scale. So basically 10 log base 10 of the value in linear scale is equal to 16 dBs, which implies x is 10 power 1.6, which is around 39.81. Okay, this is the first step we have calculated, so I'll write it here as well. This is equal to 39.81 in linear scale. Okay, now the usual method that we know is, given the bit error rate for AWGN, we can write that the probability of error in some fading channel, in our case it is given to be Rayleigh fading, is equal to your limits minus infinity to infinity, the integration probability of error in AWGN times the PDF, the probability density function of the instantaneous SNR, which is f gamma of gamma d gamma. That is the thing. So this is your performance, your basically BER performance in AWGN. That's given to us. That's the form is given to us, 4 times e power minus gamma, and this is your PDF of gamma. Okay, and now just you have to revisit the old lectures, since we are dealing with Rayleigh distribution. For Rayleigh distribution, the PDF, if you recall, is given by 1 by capital gamma, which is your average SNR, times e power minus small gamma by capital gamma, for small gamma greater than or equals to 0. It only exists in the positive half, that is a non-negative half to be precise, and it is 0 whenever gamma is negative, right? So this we saw before, just revisit your old lectures, this we saw. Okay, this is the PDF of instantaneous SNR. Now we can simply substitute this in our, we can just substitute this in this equation. So if we do that, therefore BER performance in Rayleigh fading is, so my effective unit of integration will be from 0 to infinity, because I don't need the negative part, right? The function, the PDF is anyways 0 in the negative side, so I just need from 0 to infinity. Okay, and what is PE of AWGN? It's given as 4 times e power minus gamma, correct, times, we just saw that the PDF of instantaneous SNR is given by this 1 by capital gamma times this quantity and d gamma. So you integrate this. This is integration with respect to the small gamma variable. So this capital gamma is a constant for this integral, because you are integrating with respect to small gamma, that's the variable, So your capital gamma and this constant 4 term will come out, and this is 0 to infinity e power minus gamma. If you take common, you have this d gamma. This you can easily solve. This is 4 by gamma, and this integral is actually e power minus and this negative sign will come actually. Okay, this is 0 to infinity, and you substitute the limits, so minus of minus will become plus. The first limit is, of course, if you substitute infinity, e power minus infinity goes to 0, and then we have this as the second term, because e power 0 is 1 in the numerator. So you get 4 by gamma times gamma by gamma plus 1. Gamma gets cancelled. 4 by gamma plus 1, and now gamma you can't substitute the value in the dB scale. You first have to convert it to the linear scale. That's what we did in right in the beginning. We converted from 16 dB to 39.81 in the linear scale. That you need to substitute here, which is 4 by 39.81 plus 1, and it's around 0.098015, which is approximately 0.1. okay, 0.10. So if you go to the options, see option number 1. okay, approximately it's option number 1, A, option A. So your answer is option A, this. Okay, please ask any doubts, and please for today at least stick to unmuting and asking instead of using the chat box, because it was really confusing. So at least now it seems to be not causing any trouble apparently. But yeah, please do stop me if you have any doubts till now. Simple, we have used the expression of the bit error rate in Rayleigh in fading from the bit error rate in AWGN, how to solve it. This is the general process. Now for in exam you don't have really much time, right? You have to use the known formulas and known tricks and shortcuts. So this is the shortcut method. So for this I would if you are unable to recall this, please revisit your lecture 24. okay, so we saw in lecture 24 that if your bit error rate performance in AWGN is of the form C1 times e power minus C2 gamma, where C1 C2 are constants. If it is of this form, then you can write the bit error rate performance in fading to be C1 by 1 plus C2 gamma. Again, gamma is the average SNR. okay, so now go back to our question. Here in our question, your PE of AWGN, what was the expression for that? Go back to the question. It's 4 times e power minus gamma. See, so this is 4 times e power minus gamma. Now compare these two, compare just these two, this one and this one. So you can easily tell me the values of C1 and C2. yeah, What will be C1 and C2 if you compare these two? Quickly, can someone tell me?
C1 4,
And C2?
1.
Yeah, thanks. So C1 and C2 we know now. Okay, so therefore C1 is 4 and C2 is 1. Now we can simply substitute that in this expression of beta rate performance in fading. Therefore, hence your PE in fading, here we are explicitly mentioned that it's Rayleigh fading, so I am not writing it. So if you substitute C1 equals to 4 and C2 equals to 1, you get this. See, it's again the same expression, 4 by 1 plus gamma. That's what we got previously. So again it's the same thing. Gamma we already know, I think 39.81. yeah, that's again 0.10. So both ways we are getting this same correct answer, but surely the second method is less time taking, and this is what you need to use in the exams. So easy enough, straightforward. Okay, now let's go to the second question. So for the second question, actually the second question to the seventh question, these questions are actually related, connected to each other. So the information that is provided on the top is valid for all the questions from 2 to 7. So we have a GSM system, channel bandwidth we know 200 kilohertz, operating across 10 megahertz spectrum. Communication is happening using, carrier frequency is 2 gigahertz. This information is given. Based on this given information, we need to answer the following questions from 2 to 7. Okay, so read it and read the second question. We'll go one by one. Hopefully these questions, these sample problems will give you sufficient idea to how to approach the problems in the assignments. The ultimate goal is to ensure that everyone performs well in the final exam. So yeah, so the second question, let's start with the second question. Second question is also very straightforward. The velocity of movement is given, okay, v, that v is given to be 72 kilometers per hour, okay, and we have to find the approximate coherence time of the channel. Okay, so how do we tie these two things? What's the parameter sitting in between that we need to use? Whenever there is motion, vehicle is moving, movement means there will be Doppler, FD. Okay, and from FD we can calculate our coherence time, that we know. We have seen in our lectures that there are two definitions of coherence time, right? If you recall that Bessel function, right, that zeroth order Bessel function, that was a decaying curve like that, and there are two definitions of coherence time. The first definition, TC1, says that okay, I have to consider the time duration till after which it drops to the 1 by root 2 of its peak amplitude, right? And then you equate the Bessel function to that value, and you obtain an expression of TC1 to be 9 by 16 pi FD, where FD is your maximum Doppler spread, right? So exactly, so here we will assume, let's go with the first definition. Okay, since it's not explicitly mentioned, let's go with the first definition, or if it's explicitly mentioned, we can use the second definition also, but we'll go with the first definition, which is 9 by 16 pi FD. Okay, so second question. second question, first thing which is given, V is 72 kilometer per hour. We need to find coherence time, right? And to obtain our coherence time, we need the value of the Doppler. So for that, we know that your FD, right, FD, which is your maximum Doppler spread, that is equal to FC times V by C, correct? So, and FC is your carrier frequency, correct? FC is also given in the question. Go back to the question, see, 2 gigahertz carrier, so 2 gigahertz, and C we know 3 into 10 to the power 8 meter per second. So in order to ensure that okay the units are uniform in the calculation, let's go from kilometer per hour to meter per second, because you know the numerator and denominator's units should match. So 72 kilometers per hour, if you convert to meters per second, that you can do, right? So that will be your basically 72 kilometers means 72,000 meters, and 1 hour is 3600 seconds, so this much meters per second, and this is 20 meters per second, correct? So V is 20 meters per second. We have all the ingredients with us. Now we'll just put these values. So 2 gigahertz is your FC, that means 2 into 10 to the power 9 hertz times V, which is 20 meters per second, divided by C, which is 3 into 10 to the power 8. And since I have kept everything uniformly, and instead of kilometers per hour I have switched to meters per second, so this unit of your FD will be hertz, right? Now this comes out to be actually 400 by 3, correct? 400 by 3, I think 400 by 3 hertz, which is around 133.33 hertz. Okay, so this is the first step. Now but ultimately we need to find the coherence time. So coherence time, again, since I mentioned coherence time, so from the definition 1 of coherence time, again recall lectures, it was given by 9 by 16 pi FD. You have FD, just substitute it, that is 16 pi 133.33, and that is around 1.34 milliseconds. Okay, you will get it 1.34 milliseconds coherence time. So option C, option C, option C is the answer to the second question. Okay, now the third question. Again so all the questions in the assignments are also based on the concepts that are discussed in the lecture. There's nothing which deals with any concepts which are undiscussed. So in the third question we need to find the amount of your spectral widening. So again assuming that there is single tap Rayleigh fading channel, okay, what will be the approximate spectral widening at the receiver? So spectral widening means the amount of increase in your frequency band, basically, okay, in your spectrum. So the third question, okay, I'll go to the next page maybe. So single tap Rayleigh fading channel, that is given, and just recall your lecture notes. What's the form of this type of a channel? Single tap, right? So this is your received signal, this is your channel response, which is a function of your time dimension and tau dimension, times s of t, which is your transmitted signal. And let's ignore the noise component. So you can always imagine there is a noise sitting on here, but let's ignore it for now. Okay, so this again, just recall lectures. So you see, this is in the time domain, correct? And what is this? This is multiplication. This is multiplication in the time domain, correct? And multiplication in time domain will be translated to convolution in the frequency domain, that we are familiar with. So, and that translates to convolution in your frequency domain, correct? So okay, wait, so basically we have this s of t times h of t comma tau equals r of t. Now if let's say I take the Fourier transform, so it's both ways actually, so this will be capital S of f. Now multiplication will be replaced by convolution, and if I denote it by capital H, then this just I am changing from the lowercase to uppercase for simplicity. So you get something like this. And so let's say your transmitted signal has a spectrum, sorry, oops, okay, let's say it has a spectrum like this. Okay, this is your S of AF. Let's say it's band limited from minus f0 to f0, and we are convolving this with h of f. Now you remember again in the lectures, h of f is basically your Fourier transform of the that channel response. So yeah, if you recall that the power spectral density plot, how did it look like? It looked like a bathtub or a U shape, right? So this h of f has this kind of a nature, and the asymptotic limits, the extreme points were minus fd to fd in this range. So this, if you do this, then what kind of plot will you get here after doing your convolution? So we know that the duration actually, if we talk about the time domain, then if we have one signal of duration t1, another signal of duration t2, and if we convolve them, then the overall signal, the resulting signal, has a duration of t1 plus t2. So obviously here also there will be spectrum widening, right? So the width of your resulting band, so that will cover from, so this fd will get added to your f0, correct? So that will be, it's not drawn to scale at all, but okay, so this point, this is minus f0 minus fd, and this point is f0 plus fd, okay. This is your, okay, let me call this is r of f, okay, yeah. So this is the result of your convolution, and you see there is increase in the spectrum, there is widening of spectrum, that's why it's called spectral widening, okay. Everything has been discussed by Professor David in the lectures. Now if I ask you what is the amount of your spectral widening, so in the question also they have asked the same thing, what is the approximate spectral widening. So you see both on the positive side as well as on the negative side there is increment by fd amount. So overall what is the increment? 2 times fd, correct? So that's your spectral widening. So therefore spectral widening is twice fd. So the reason which I just told, that because we have fd increment on either sides, so, and this is 2 times, how much is fd? Fd we already calculated in the previous question, right? So just go back, fd was this 400 by 3 hertz, right? So fd we have already calculated 400 by 3 hertz, and this is twice of that, which comes out to be 266.7, and we can approximately say that okay, 276 hertz, because in the question also we need to find the approximate, right? Approximate spectral widening. So you see all values are given in integers, so we are approximating the decimal places. So this is approximate spectral widening, which is 267 hertz, and if you compare with the options, it is option A. It is option A, twice the Doppler. So this is option A. That's your answer. Great. Okay, let me just check. People are there. Okay. Good. So yeah, we're done with the third question as well. Okay. Again, it's a continuation of the same. So now let's look into the fourth question. Read the fourth question. So you are introducing frequency hopping into the system, going to a different frequency so as to avoid your fades. Okay, if your current frequency goes to a fade, it is gone, so you need to go to a different frequency which will avoid the fade. Okay, and you will have a good channel there at that frequency. So the assumption is that okay, there is at least one good GSM channel at any instant of time. So frequency hopping will work. And what should be the hopping rate? Okay, how many hops per second do you need to do in order to avoid the fade? That is the question, and this is very simple actually. So this is directly tied to the concept of your coherence time basically. So you know that what is the coherence time? Coherence time is the duration for which the channel remains invariant or constant, or in other words, after a duration of coherence time we observe a significant or a substantial change in the channel. So after the coherence time duration, my channel is channel is prone to go into a fade actually. So my hopping rate should also be in sync with that coherence time. So in every coherence time amount of time, after every tc seconds, coherence time seconds, I should hop once, change to a different frequency. So that should be the hopping rate, right? And that way I will avoid the fade. So okay, fourth question, right? So you're introducing frequency hopping to avoid fades. Okay, so in order to avoid the fade, what should be the hopping rate that's being asked? So we should hop once in okay wait okay, there seems to be some issue. Okay, today it's really a hard day for me. Doesn't seem to work. There seems to be an issue with this. I don't think I will be able to save this document, unfortunately. So it's still unsaved. I don't think it will be saved. So yeah, it's hung there forever. So anyways, at least you will have the recording with you. So So what can I say? Okay, we are in week 6.
Sir, excuse me, sir.
Yes.
Sir, every week, Sunday, Monday, Tuesday, these 3 days, these classes are going on, sir. But in the NPTEL portal, where we are, these lectures are kept, sir.
Okay, so
I didn't find anywhere.
okay, so you go to the course web page. This is the course web page.
Yes, sir.
Now on the left hand side, you will have this course outline, these things, right? See, course outline, week 1, week
Okay.
2, like this. Just scroll down, and in the end you will find this problem solving session, July 2023, the last menu. Okay, my cursor is in just above that, so you click that problem solving session. Okay, it will give one
Okay.
checkbox. Again click it, problem solving session recording. So okay, now you will find another link to view the
Okay, sir. Okay.
okay, then actually you will be able to see an Excel sheet or a Google sheet where the separately the sessions are present for Monday, Tuesday and Sunday.
Okay, sir. Okay.
Yeah.
Thank you, sir.
So there are the YouTube links also, the links to the recordings, as well as the presentation folder also, where we can find the lecture notes and all right. So okay, sorry for this this document didn't save the previous one. So anyways, just refer to YouTube video for question 1 to question 3. Okay, so we'll start from the fourth one again. So fourth one, as I was saying, what is the hopping rate? So as I already said, okay, this one isn't working, so I'll just close this. It's not working. It's not even closing. Okay, anyways, let's start with this fourth question. So the fourth question, we have frequency hopping is incorporated to avoid fades. Okay, so fades, and the rate of hopping, we should hop once in every coherence time duration, because what I said is, after every coherence time my channel will substantially change and my channel is prone to go to a fade. So at least after every coherence time I should hop once. That is the idea. Okay, so we should hop once in every coherence time, because the channel changes substantially after coherence time. Okay. Maybe I'll just highlight this as well so that people don't get confused. Okay. Alright, so therefore based on this information, what is the hop rate? This is basically one hop in every coherence time. This is TC. TC is your coherence time, basically the reciprocal of your coherence time. So this is one hop, and coherence time just okay. Now that previous PDF we can't access, but if you remember that we actually calculated the coherence time in the second or the third question, I think in the second question. Yeah, so coherence time we already calculated, and it was 1.34 milliseconds, and this we obtained, so one hop in this much seconds, and if you solve this is approximately 746 hop per second. Okay, that's the hop rate, and yeah, this is option D. So 746 per seconds, 746 per seconds, and that is option D. Okay, I heard that notification sound once again, so let me check if again. Okay, I think this time someone has really wrote something in the chat. Okay, is there anything? Oh yeah, thanks. 1.34, yeah, so good, good Anandan, thank you. So yeah, thanks for following. So yeah, so we get option D. Fine. Now, so we are done with the fourth question. Now let's go to the fifth one. Okay, maximum number of fades per second that can occur using the expression for NV. That NV, you remember, there was one term that we used for NV, that is LCR, or level crossing rate. So if you remember, there was a threshold, right? There was a fade threshold denoted by VTH, and your signal is continuously fluctuating. Sometimes it's above the threshold, sometimes it's below the threshold. Whenever it's below that threshold, we consider it to be the region of fade, and the number of times the signal actually crosses that threshold level is actually the number of level crossings, basically. So the level is that threshold, VTH. So we looked at all these things. So NV is your level crossing rate, or LCR, and we had a explicit expression for NV, which, if you remember, was square root of 2 pi times FD, maximum Doppler, times rho times e power minus rho square. This much fades per second. Now what is rho here? Rho was that ratio of your V TH by V RMS, if you remember. So I'll write it down. Everything has been discussed in the lectures, but still. So this is your LCR, or level crossing rate, which is denoted by NV, and this is the formula for NV. This much fades per second. Okay, so here FD again, you already know it's the maximum Doppler shift. Rho is your that ratio of VTH, threshold voltage, to the RMS voltage, and so this is the number of fades per second, level crossing rate. But there is one more thing which is mentioned, which is maximum. Okay, you need to find the maximum number of fades per second. So in other words, you have to basically maximize your NV, correct? So you need to find maximum number of fades per second. That is asking the question. So maximum number of your level crossings basically. So in order to maximize something, what we do from the basic knowledge of calculus, we always differentiate that function and equate it to 0 to find the maxima. So similar strategy can be done here. So if you have this is the known expression for NV, right? And in order to maximizing for maxima, you differentiate with respect to the variable rho and equate it to 0. And if you do that, so this square root 2 pi FD, this term is just a constant, so it will come out. You differentiate the remaining term, which is this equal to 0, and this will give you square root 2 pi FD times, again follow that chain rule of differentiation. So these are new things, nothing new things. So there's no need for me to work out these steps, but still, in case somebody was unable to understand how that 1 by root 2 came, so hopefully by now it should be clear. Okay, so this we factorized it and we have that equal to 0, and this term, this can't be equal to 0, right? This is not 0, so obviously we have to equate the remaining term, which is 1 minus 2 rho squared, that equals to 0. So go to the next page. This means your 1 minus 2 rho squared equals 0. That means rho square equals half, or the rho is 1 by root 2. So that is the idea. So and rho, remember, rho was, the definition of rho was this ratio VTH by VRMS. So whenever rho is equals to 1 by root 2, when your threshold is 1 by root 2 times your VRMS, then I will get maximum number of level crossings or maximum fades per second, correct? That is the idea. So diagrammatically, if you have a signal like this, random fluctuations, like this, and let's say if this is your VRMS, then 1 by root 2 of your VRMS somewhere below it, which is like this. Okay, so this point is VRMS by root 2, and that is equal to your VTH, and this, at this level you will see your maximum number of level crossings. This is 1, this is 1, this is 1, this is 1, and this is 1, this is 1, and so on and so on. This is 1, this is 1, this is 1, this is 1. So that's what it's happening here. Okay, all right. So at rho equals to 1 by root 2 you have this. So therefore just calculate the value of NV at rho equals to 1 by root 2. So maximum NV or level crossings occur at rho equals to 1 by root 2. Therefore your NV is equal to, the max actually is equal to square root 2 pi times FD. FD was 400 by 3 hertz times, see the expression, rho times e power minus rho square. So we'll put rho equals to half, sorry, rho equals to 1 by root 2. So that becomes this, and that is approximately 143 fades per second. Fine. Whenever your threshold is 1 by root 2 times your VRMS, you will have maximum level crossing rate, right? And that is at rho equals to 1 by root 2 basically. So we just did that. Okay, how that 1 by root 2 is coming, I just differentiated it and showed you. So that's not really very important, but yeah. Okay, great. Let's quickly run through the remaining problems as well. 6 and 7. So 6, question number 6 says that, okay, in question number 6 we need to find the expected fade duration. Again, this was also discussed. So NV was your level crossing rate, LCR, and expected fade duration, again expected fade duration means average duration of fade, right? So expected value, average value, expected fade duration is the ADF or average duration of fade, that we need to find. And we are mentioned that the VRMS is set as the threshold. So VRMS is equal to the V threshold, VTH, and from that you can easily conclude that what will be rho, that's the ratio of them, so that will be 1. We already know the expression for expected fade duration or the ADF, average duration of fade. Just plug in the values there and we can find its value. Again, this one is also very straightforward. The thing which is mentioned here is, and please interrupt me if you feel that I am going a bit fast. The reason why I am going fast is because these are very straightforward problems. It doesn't take much time. So in case you are unable to follow, just unmute and stop me if you have any queries. So your VRMS is set as the threshold that's given in the question, and that means your VTH and VRMS are equal. That means your rho, which is defined to be the ratio, is 1. Now we are asked to find the expected fade duration. In other words, average duration of fade. or which is abbreviated as ADF. And if you again recall the lecture notes or the lecture videos, so the notation that Professor David used was this T bar. This bar denotes the average actually. Okay, T is the duration, so it's the average duration of fade, and the expression that we got was e power rho square minus 1 in the numerator divided by square root 2 pi times fd times rho. That was the expression for ADF, average duration of fade, and here rho is 1. So you just simply put rho equals to 1. So you get in the denominator you get square root 2 pi fd, since here rho equals to 1. And again fd you have already calculated, the value was 400 by 3. Okay, okay, wait, let me admit. Okay, good. Now so we have all the values, and it's a simple calculation will actually give you that this is 5.14 milliseconds, which is approximately, you know, up to 1 decimal place you can approximate it to be 5.1 milliseconds, and that's your average duration of fade, which if you just check with the options, it is option C. Okay, 5.1 milliseconds. Okay, be careful, it's not option D. Option D has units in microseconds, but our answer is milliseconds, so 5.1 milliseconds, option C. So option C is the answer. Great. Now go to the 7th question. Read the 7th question.
Sir, in previous problem, how you have taken E value, sir?
Oh, E is actually that exponential. E is that your 2.718, that non-terminating, you know, that exponential, you know, the log base E we take, right, that E. So you just put this E, substitute here. E is your exponential.
Okay, sir.
Okay, the one which we are familiar with. Whenever we talk about, you know, natural logarithm, the base is E, the exponential. The exponential, you know, is encountered in lot of places. Of course, in, you know, this expression for PDFs and all these parameters, we will have, you know, E extensively used. So yeah, that's that 2.718 and so on. It continues like this. That's the E that you have in your scientific calculator as well. Anyways, so and E is not any variable, please. Yeah, thanks for, you know, asking this. E is not the variable. E is just this exponential constant, that constant that we know, mathematical constant. Okay, let me admit. Right, so in the 7th question, okay, what we have to find ultimately in the 7th question is the approximate throughput per user. So throughput is the useful data rate, right? And the maximum data throughput, that is per time slot in GSM, that is allowed is like 22.8 kbps, but you won't be able to use this maximum data throughput because of the fact that your channel will be in fade for a certain duration. We saw just in the previous part, right, that there is some average duration of fade, right, where the signal is below your threshold. So you have to take care of those parts. So effectively the part till which your signal is above the threshold, your signal is not in fade, that will give you your actual approximate throughput, useful throughput. So it will be effectively a fraction, some fraction of 22.8. That's the maximum allowed. Okay, 22.8 is the ideal scenario where we have no fade. Okay, so it will be overall your net throughput will be, approximate throughput would be some fraction of 22.8. It will be less than 22.8 kbps. Let's look at it diagrammatically. So I think we are in question number 7, is it? Yeah. Again, recall lecture. So all the numericals, conceptual questions are based on the concepts that are discussed. Okay, so if we have a signal like this, so on, if I consider my threshold to be this is my PTH, let's say. This axis is amplitude, the y-axis amplitude of your signal, the horizontal axis is your time axis. Now this duration, see, the portion for which the signal is below my threshold, so this is one such region. Similarly this is another such region, similarly this is another such region, correct? These are regions of fade. So the first fade has duration, let's say T1, second one has duration, let's say T2, third one, let's say, has duration T3, and so on. I mean, you can continue. And let's say the total time for which you observe is, let's say, total time of the time duration of the signal is, let's say, capital T. Okay, it's a capital T. Okay, so your probability of being in fade actually is essentially equal to the probability that your V is less than or equals to VTH, correct? That's the probability that you will be in the fade whenever your voltage or the received signal amplitude is below the threshold. Now what is this form actually? This is a known form, this is a very familiar form to us, which is actually your CDF, right? Whenever we talk about CDF of a random variable, so that's denoted by this, f of capital X, that's your random variable, less than or equals to this is actually f capital Fx of x, like this. That's your CDF. That's how we denote, right? So this is my CDF of this random variable v, correct? This is effectively the probability of it is what? So out of this, if I talk about with respect to this plot, so out of this total capital T duration, how much time am I in the fade? This T1 times plus T2 times plus T3 times divided by the total time, correct? That is the probability. Or using summation, I can write Ti summation I. Here I am considering 3 components, so I running from 1 to 3 by capital T, correct? Now this CDF, just the notation that we are familiar with, I wrote it here, capital F. So that means it is the same as capital F subscript capital V, that's the random variable, Vth, right? That's the CDF of V. And this fading that we have considered is the Rayleigh fading. And again, revisit your earlier lectures. The CDF, the expression for your CDF function was for Rayleigh fading was actually discussed, and that took a form like this, which is 1 minus e power, again e is that exponential, okay, the 2.71, that constant, mathematical constant, 1 minus e power minus Vth by Vrms squared. This is the expression for CDF, and Vth by Vrms is what? That is rho, right? We have defined rho previously also. See, rho is the ratio of the threshold voltage to the RMS voltage. So this we know, this happens for, this is the Rayleigh CDF, okay, Rayleigh fading CDF, expression for the Rayleigh distribution CDF. So that's it, that's actually your probability of fade, okay. Now the additional information that is given here in question number 7 is that Vrms is set as the threshold. That immediately tells you about rho. So Vrms is said to be equal to the V threshold in our problem, which implies your rho, which is again the ratio of these two parameters, is equal to 1. Now just put rho equals to 1 here, substitute. I mean, not just substitute, so yeah, you effectively need to substitute only, but so the thing is, therefore what do I get as the probability of fade? So far I have calculated the probability of fade, right? Which took this, I started with here, right, probability of fade. I observe this plot, and then I observe this, you know, this is a CDF expression. I know the expression for CDF for Rayleigh PDF, and in problem it is mentioned that Vth and Vrms are equal, therefore rho is equal to 1. So probability of fade in our problem, which corresponds to rho equals to 1, would be 1 minus e power minus 1, because rho is 1, right? Since rho is 1, in our problem, and that is 0.632. that is your probability of fade. Okay, the fraction of time in which it stays in the fade below the threshold. But for throughput, for transmission, we need a non-fading scenario, right, when my signal is not in fade. So therefore probability of no fade, and no fade, for no fade, actually why do I need no fade? For my useful throughput, then only I will be able to send my data. So for my useful throughput, I need to ensure that there is no fade, and what will be that probability? Is basically the complement of the fading probability. So that is 1 minus the probability of fade, which is 0.3678, like that. Yeah, 0.367. Now you are done. Now your approximate throughput, your effective throughput per user is this probability of no fade times your maximum data rate, or the maximum throughput that is allowed, which is this 22.8 kbps, times your max throughput. Okay, I'll go to the next page because we have run out of space. So what was the probability of no fade? That is 0.367879 times the maximum throughput that was given in the question to be 22.8 kbps, and this is approximately 8.39 kbps. Okay, so you see 8.39 kbps is actually the effective throughput, which is less than your maximum that's possible, which is 22.8. so option D is the answer, right? 8.39 kbps. So option D. So it's easy what we did. So you first calculate the probability of fade, then for throughput you need to find the probability of no fade, take its complement, basically 1 minus that probability of fade. That will be your fraction of useful data actually. So and you multiply that probability of no fade with your maximum throughput to get the net effective throughput, correct, which is 8.39. Simple, straightforward. So we are done with question number 7 also. Okay, let me just check quickly if people are there. Okay, so I'm assuming everything is okay so far. So since
Sir,
yes,
excuse me, sir. Yeah, sir, throughput means what you have to get exactly? Approximate throughput.
so throughput is basically your useful data rate actually. So in your that coherent detection also, sometimes we saw that okay, some part of the frame is reserved for your channel estimation. Whenever you will be doing channel estimation, that is dedicated to your channel estimation, if you recall the coherent detection, and the window in the entire coherence time window, we have some time reserved for the channel estimation, that is your training, and the remaining time is actually data transmission, that is your effective throughput. So here actually out of your 22.8 kbps, that is maximum allowed, you are actually effective able to transmit 8.39 kbps. So that's actually the net, I would say, useful data rate kind of thing, in very layman terms I can say. So that's the thing. So that's why you are
So
redacting.
it is yeah, means useful data transmitted.
Exactly, because you see, whenever there will be fade, that's of no use, right? So we have to consider only the portions where whenever the signal is above the threshold. So that fraction we are assuming out of the entire t duration, we are only assuming the fraction which is whenever the amplitude is above the threshold. So that's why we are getting an effective value which is lower than the maximum allowed, right? So that's the
Okay. Okay.
useful data rate actually. Yeah.
Okay.
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 Yeah. So I just described it in very, maybe not a very good way, but you can refer to the standard textbooks like Rappaport or Molish or any other books, Proakis and Goldsmith, any book to know more on these things, details of it. Always a good exercise to know more. But yeah, for a very basic overview, I think this is okay. So yeah, so after question 7, now let's look at question 8. Yeah, please read question number 8. These are conceptual questions. You can answer me also this questions. These questions doesn't really involve much of mathematics, so you can simply answer me also if you want. Question number 8. Okay, hopefully everyone has read the question number 8. What is the setting? We have a base station and a mobile system with two antennas. Mobile system has two antennas, two receiving antennas are there. The transmission from base station is picked up by both the antennas in the mobile system, which experience different channel conditions, of course. Okay, so the two antennas in the mobile system will have two different channels from the base station. They will experience different channels, and hence different values of instantaneous SNR. That instantaneous SNR, if you remember, that small gamma. So both will be different channels, and obviously they will have different instantaneous SNR. Let's say gamma 1, gamma 2, like that, for channel 1 and channel 2 respectively. Now it is mentioned that the SNR for both the antennas is below the threshold at which the signal can be properly detected. If it so happens that the SNR for both the antennas, say gamma 1 and gamma 2, are less than the threshold, that's the minimum signal strength that is required to be properly detectable, then what kind of diversity technique can I use, can help me actually in this situation to get a proper detection of the signal? Is it selection diversity? Is it optimal diversity? Is it both A and B, or is it none of the above? Okay. Okay, so let's look at it, the diagram. Okay, so this is your base station, let's say, let's say this is your mobile system, and as mentioned in the problem, it has two antennas. This is one, let's say this is the second antenna, so I'll call it 1, and this is 2, antenna 1, antenna 2, and is receiving the incoming signals from the base station like this. Fine. Now these two links are two different channels corresponding to the two receiving antennas, and they will have different instantaneous SNR, obviously, because they are different channels. If I denote their respective instantaneous SNR to be gamma 1 and gamma 2, okay, so let the instantaneous SNR for the two antennas be gamma 1 and gamma 2 respectively. Okay, that's what I have denoted in the figure. Okay, now we need to find whether what will happen actually in this scenario, which diversity technique will actually help us in detecting the signal better. In the question it is mentioned that SNR for both the antennas is below the threshold. Threshold is the minimum signal level that I need for detecting the signal properly. So that's the minimum I need. If both gamma 1 and gamma 2 are below the threshold, then what diversity technique can I use? Okay, so let's first look at if we can use selection diversity or not, then we will check if we will be able to use optimal diversity or not. Okay, so in selection diversity we are just checking if selection diversity will work or not. Okay, in selection diversity, again go back to your lecture notes, you pick the SNR. Okay, you pick the SNR out of these two channels, out of these two SNRs, you pick the one antenna which is having the higher SNR in selection diversity, as the name suggests. Also you're selecting, so selection diversity, selecting the best one out of the two, whichever is greater you pick that. If gamma 1 is greater than gamma 2, you pick gamma 1. If gamma 2 is greater than gamma 1, you pick gamma 2. Okay, that's the idea of selection diversity. So in other words, the for selection diversity your gamma will be the maximum out of the two, max of gamma 1 comma gamma 2. Correct? Now in the problem it is mentioned that both gamma 1 and gamma 2 are below the threshold. Okay, so now you tell me, if both of them are below the threshold, will this selection diversity help me? If it helps, how will it help me to detect the signal? So gamma 1 and gamma 2, they are less than your gamma TH, that's the threshold, that's given. Now tell me, now, so does this selection diversity turn out to be useful in this case? Obviously no, right? Because if both gamma 1 and gamma 2 are lower than the threshold, even if you pick the maximum out of the two, it's still gonna be less than the threshold, because both are less than the threshold. So if your SNR is below the threshold, then obviously you are unable to detect the signal properly. So selection diversity won't work here. So in words I should write that since both I am just restating it. Since both gamma 1 and gamma 2 are below threshold, so this threshold means actually gamma th, the minimum SNR required for proper detection. Okay, that's the minimum I need. Since both gamma 1 and gamma 2 are below the threshold, at which the signal can be properly detected, therefore this max of them will still be lower, right? Will also be below the threshold. Correct. So hence selection diversity is not going to work here. Correct. So for a sample case, you can take the example, if okay, this is aside, okay, this is just for illustration. Let's say, for example, based on this scenario, if your gamma th is, let's say, the minimum threshold that you need is 10 dB, this is gamma dB, okay, this is the V, and if your gamma 1 is 6 dB, gamma 2 is 5 dB. Okay, so both gamma 1 and gamma 2 are less than the threshold. So the maximum of them is gamma 1, which is 6 dB, but that is still lower than the threshold, right? So selection diversity won't work. Correct. Now, so we have concluded that selection diversity won't work. Now the other type of diversity that we know is the optimal diversity, and in optimal diversity, what happens is that initially you took the maximum out of the two SNR, but in optimal diversity you take the sum, you combine them and you take the sum of their instantaneous SNR. Okay, now it is mentioned that both gamma 1 and gamma 2 individually are lower than the threshold, but there is a possibility that their summation might cross the threshold, actually might be actually greater than the threshold, right? So for instance, here in this example which I kept it here in the box, if you do gamma 1 plus gamma 2, that is actually 6 plus 5, which is 11 dB, which is actually greater than your gamma threshold. Hence it is above the threshold and you will be able to detect the signal properly. Okay, whereas max of gamma 1 and gamma 2 was actually 6 dB, which was less than threshold, and that is why actually your selection diversity didn't work. Okay, so in optimal diversity there is a chance that you will be able to detect properly, because here the value of this gamma 1 plus gamma 2 may exceed or cross the threshold. Okay, and hence,
Sir,
yes.
sir, here in optimal diversity, what do we exactly do so that we are getting taking this gamma equals to gamma 1 plus gamma 2?
Okay, that is that has not been discussed in the lectures, and even I am also not familiar with those concepts. All you need
Okay.
is this concept that, okay, expression that we have. In the first case we are just picking one out of the two. In the second case, oh, there's a lot of, I mean, technologies and all going on behind how we do this. And I think
Mm-hmm.
optimal diversity is also, known as the maximal ratio combining actually. So here you are taking the maximum, you are combining these two instantaneous SNR together, so that your resultant is actually a higher value that is, expected to cross your threshold. So that's a better diversity setting in this scenario actually. So that your at the receiver end, that the SNR that you get will be sufficiently larger than the threshold. That's the minimum that you will need to detect. So I won't go into the, details of how exactly you are getting this gamma 1 plus gamma
Yeah,
2, but yeah,
yeah.
just.
Sir, because generally in MIMO antennas,
Mm-hmm.
we use this selection diversity. Na? So multiple antennas are kept at the receiver, and then the antenna which is getting maximum signal
Yeah,
amplitude,
yeah,
that is selected.
yeah.
So, so that is okay. But then, how do we implement this diversity, optimal diversity? That is the question. Okay,
So
so
for I think, again, you can refer to any textbook also for this. I mean,
uh,
the reason why I'm not going into the details,
yeah,
because
yeah,
that was not actually discussed in the lectures also. So
yeah,
as an exercise, anytime I think this will be mentioned for diversity techniques, these things will be mentioned in the textbooks, in at least one of
mm,
the textbooks. So you can definitely, go through that in your leisure time. And yeah,
yeah.
so yeah, yeah, yeah,
Okay, okay, sir.
yeah. So the optimal diversity, hence optimal diversity in this case may actually work. Okay, yeah, and so you can refer to textbook to know more on diversity. Okay. Um, so in the last lecture also, I think someone was asking about de-interleaver, how it's working and all. So again, those things were not covered in the lecture, and of course, um, this field is also not related to my own area of research as well. So I am also not familiar with it. So we let's just stick to the contents that are covered in our course. Okay, and we all of us have the textbooks and all. There is internet also, we can just make use of it, to know some additional information. It's definitely good, definitely good. So that we can do, you know in our free time. So good. Okay, so the conclusion is that optimal diversity may work here, selection diversity won't work here. So in question number 8, okay, which of the diversity technique may lead to, so whichever diversity has a chance, so it's option B, optimal diversity has a chance. So optimal diversity, so answer is B, optimal diversity. And now going to the next question. So this was an application where actually selection diversity is not a good choice, so whenever both are less than the threshold. Okay, and the ninth question, assume that, so that's an extension of the previous question only. Assume that one of the antennas experiences SNR which is above the required threshold. In the previous case, both were below the threshold, but in this case, one of the antennas has instantaneous SNR above the required threshold, while the other antenna does not have that. Now here, which of the following diversity technique will lead to a proper detection of the signal? Okay, so that is being asked. So
Selection diversity, sir.
I mean, both will work, right? Optimal will also work, right? Optimal is taking the sum of the two. So here selection will work. You are right, because one of the SNR is greater than the threshold. So obviously, even if the other one is below the threshold, I don't care, because I am taking the maximum one out of the two. So selection will certainly work. Exactly. And
Both will work.
yeah, that is the thing. So option C is the case. Both will work. Okay, so here actually both will work. So the idea is actually, so here the given situation is if one of gamma 1 or gamma 2 is above threshold. I'm just writing these notes so that later on, if you watch it, you will be able to relate it in a convenient way. So then if one of them is above the threshold, then obviously my max of them will also be above threshold. Correct? So therefore selection diversity works. Also, the sum gamma 1 plus gamma 2 will definitely be above threshold. Okay, so optimal diversity also works. So both will work actually, which is your option C actually, both A and B. Okay, and as an example, as a sample case, you can take, let's say, gamma th equals to 10 dB, yeah, gamma 1 equals to 12 dB, which is greater than your threshold. One of them is greater than your threshold, whereas another one, let's say, is lower than the threshold as per the problem, let's say 7 dB. Now here, okay, gamma 1 is greater than gamma th, gamma 2 is less than gamma th. Okay, so gamma 1 plus gamma 2 is 19 dB, which is of course greater than gamma th. Therefore optimal diversity works, and of course max of gamma 1 comma gamma 2, which is actually gamma 1, is again greater than gamma th. Therefore selection diversity also works. So yeah, okay, so this was very easy. Okay, and I'd like to end today's discussion with this last doubt clarification. So I found one doubt in the discussion forum. Someone was willing to know why is the moment generating function so called, what is the significance of the name, logic behind the name. So this is more of a mathematical question. It's not very much related to our wireless communication concept, but I'll try to answer that as well. Okay. Okay, so question number 10. So this is doubt clarification on moment generating function or MGF. Okay. Okay. So moment generating function, let's break it down. So what are the three parts? Moment, generating and function. Okay. So first we need to find moment. Okay. What is your moment? What do you mean by moment in mathematics? So okay, so it's not the commonly used English word in the dictionary. It's not the same as moment, but like capturing a moment or like that. It actually has a mathematical definition. So the idea is the nth moment of a random variable let's say capital X, that's the random variable capital X. The nth moment of the random variable X is defined as expectation of x power n. Okay, those who are from have some have done some courses on probability, random processes, they might be familiar with it, but just just to clear the doubt, I wanted to address this. And this is actually around 0. If it's around some mean, then it will be like expectation of x minus mu whole to the power n. Okay, where mu is your expectation of x, the mean actually. But here we are assuming mu equals to 0, around 0, that's why we are taking expectation of x power n. That's the definition. Okay, I just remove this so that you guys don't get confused. So this is the definition of nth moment. Okay, so the other one which I showed x.
Sir, what you have written in okay, around 2. Okay.
No,
Okay,
not
sir.
around 2. Wait. This is around 0.
Okay, it is around 0.
Around 0. The meaning is here this is what? This is actually expectation of x minus 0 whole to the power n. The same thing. Correct? These two are same thing, right? So that's why around 0. This is the 0. Okay. If so the central moment, if you talk about some finite value instead of 0, if you talk about some mu or expectation of x, then it is called nth central moment. Okay, nth central moment of random variable x, that is defined as expectation of x minus mu whole to the power n, or which is mu is basically your expectation of x, which is x minus expectation of x whole to the power n. So this is around mu. Okay, that you get the idea. So this is around 0. So this is just an aside. Let's stick to this one only. Okay, for our simplicity, let's look at only moment, not central moment. Okay, so far so good. So this is the definition of nth moment. Easy. Expectation of x power n, that is the definition. So I'm writing it again. Nth moment, forget central moment, don't get confused. This is just, since you want to know, I have written this. Nth moment is nth moment of x, actually, yeah, is expectation of x power n. That is the definition. No problem with this. Okay, so the thing is, okay, so the first moment, if I ask you what is the first moment of x, what is it? You know, nth moment of x is this, given by this expression. What is the first moment of x? If I ask you, what does that mean? Yeah, if I ask you what is the first,
Expected value of x.
exactly, you put
Yes.
n equals to 1, that's it. That's the first moment of x, that is expectation of x, which is mean, which is your mean expectation. Similarly, if I ask you what is the second moment of x, that is expectation of x squared.
N is equal to 2.
Exactly, n equals to 2, and that is your variance, actually. Okay, similarly, so there are other terminologies as well. So at n equals to 1, you have your first moment, okay, which is your mean, basically expectation of x. If you put n equals to 2, you have your second moment, okay, that is your variance, because expectation of x squared. Okay, so this is your expectation of x, this is your expectation of x squared. If you put n equals to 3, there are other terms as well. Okay, let's not go into the detail, I'll just mention their names. Qness, and you can go further, this is called kurtosis, and so on. Okay, but you get the idea of nth moment. Great. So first part of the MGF, we have decoded the meaning, what is moment. Now generating is the second part. So this is a function which generates the moments, okay, generates these nth moments. Such a function is called moment generating function. Now how is that happening? Okay, let me show you. So again, the first moment, which was the mean, right, is expectation of x. In terms of integral, how do you define it? You integrate from minus infinity to infinity, you take the value of the random variable, you multiply with its PDF and integrate like this. That's how you define your mean. Similarly, variance, how do you find expectation of x squared? That is minus infinity to infinity, again you take x squared, take the PDF, that's it, that's the definition, mathematical definition. Fine. Now MGF, again recall your next lectures, recall lectures. What was the expression for how did we denote MGF in the lectures? We denoted with this psi variable, psi suffix x of s. X is your random variable, Ax is your random variable. Okay, sometimes you can find in some textbooks the notation m as well, mx of t or something like that, mx of x or whatever. Okay, so notation is not very important here, but I am sticking to the notation that was used in the lectures. Okay, so psi x of s, and how was it defined? The MGF, expectation of e power sx. Okay, So again, expectation, we know the formula is like this. We take the value of the variable, multiply it with its pdf of x and dx integration. Okay, but this is what is important. This we know from our lectures. Okay, now you see it's expectation of a exponent, right? E power sx. So e power x, you know the formula of e power x, correct? So what is the formula of e power t, let's say, the exponential series? Yes, someone can you quickly say, tell it? E power t or e power x, what is the formula? What is the expansion? What's the series? What are the terms? It's an infinite series, right?
1 plus x square by 2 plus
So here if I am taking t as the variable, so 1 plus t, sorry 1 plus t plus t square by, actually it's t power 1 by 1 factorial, which is the same as t, plus t square by 2 factorial plus t cube by 3 factorial, and so on till infinity. That's the formula that we are familiar with. Now how can you expand this moment generating function? It's also the expectation of e power something, right? So this is what expectation of, if you expand the series, it will be 1 plus sx plus squared term, right? A squared x squared by 2 factorial, then the cube term by 3 factorial, and so on. Okay, now what is this? Use linearity of expectation. You can take the expectation separately and add them together. So if you do that, expectation of 1 is 1 plus expectation of s times capital X. So s is just a constant, it will come out. So you get this for the second term, and for the third term, similarly, what will you get? A squared by 2 factorial will come out as a constant coefficient, and you get expectation of x squared plus, similarly, this is x cube fine. Now you see, already you can see what is this. This is your first moment, right? This is mean, that's your first moment. This is what? This is a variance, second moment. See, already all these things are hidden within the NGF. Okay, I just expanded it and I found this hidden. Now how can I get, since it's a moment generating function, so it has to generate the moments, right? Nth moments. So if I talk about the first moment mean, how do I obtain the first moment mean from the expansion of MGF? See, if I have to find this E of x, all I need to do is differentiate this entire thing, differentiate this entire series with respect to s, and evaluate it at s equals to 0. Do you agree with this or not? Wait, all I am saying is you differentiate this MGF with respect to s and evaluate it at s equals to 1. I claim that will give me expectation of S. Does everyone see this? Is everyone able to see this last step?
Yes, sir.
Fine, that is easy.
Yes, sir.
Okay, similarly, so this took care of our first moment. How can I find similarly the expectation of x squared following the same logic? Tell me. What will be the expression for expectation of x squared?
D2 psi of x of s
Ah,
upon ds square.
yes. So we take the second derivative, and of course evaluate it at s equals to 0. Why we have to evaluate at s equals to 0? We need to ensure that the higher order terms, they will, you know, vanish, because if you do the double derivative of this expansion, of course the first two terms will die, they will be 0. The third term, which is s squared, that will, you know, s squared by 2 factorial, if you differentiate it twice, it becomes 1, right? So you have expectation of x squared exactly. But for the next term, which is s cubed by 3 factorial, if you differentiate it twice, there will be a factor of s, right, which will be still there. And similarly there will be other terms of s squared, s to the power 3 on the successive terms as well. So in order to vanish them, you put s equals to 0. Okay, that's how you find that particular nth moment. Okay, so similarly with this logic, in general, expectation of x power n is equals to the nth derivative of your MGF, again evaluated at s equals to 0. So you see, so this was the second moment, and this is your nth moment. So therefore your MGF is generating, the MGF generates the nth moments of the random variable, okay, random variable x. Okay, that's why it is known as moment generating function. So you're able to, you know, generate all the uh, moments corresponding to n equals to 1, n equals to 2, whatever. Okay, so that's the rationale behind calling it moment generating function.
Sir, excuse me, sir. What you have called third movement and fourth movement? Yes, here
Oh,
on that
that's
page.
it's called skewness, the usual terminology. The third moment is skewness, and the fourth one is kurtosis. Okay, okay. Anyways, those are beyond the scope of this course. So, yeah. So, mainly mean and variance. I think in wireless, we restrict ourselves within the second moment only, because all the PDFs, CDFs that you have discussed are, you know, the parameters of interest for us are the mean and variance mostly. We don't usually go beyond n equals to 2. So
Okay.
yeah, this is just for, you know, terminology I've just mentioned. But anyways, so you get the idea, right? That's why it's called the MGF. Okay, so I think with this we have come to the end of today's discussion. So unfortunately, actually, the first document actually got frozen, and the first three questions were not saved. So I've mentioned a note here in the beginning of this fresh PDF file, that you can refer to the recording anyways, to see the solution of the question number 1 to 3. So unfortunately
Sir,
only.
will you please share the link here itself?
What do you mean here itself?
Can you please share the link video YouTube link of this session?
Yeah, I do share it, right? I upload it in the main sheet in the course web page. You can access it from there, right? This problem solving session, these recordings in the course web page, it's available, right? So this
So
sheet is,
immediately it will be available.
yeah, obviously, since I actually update the sheet, every TA does
Uh-huh.
that. So firstly I upload the video on YouTube as well, and I also parallelly update the sheet as well. I share the links, so it's updated. See, if I click it, wait. So mine is Tuesday's session. The first one is Monday's session. I think so. Sorry, Sunday's sessions. But mine is the third one. You scroll down, the third one. See, this is my name, Avik Mukhopadhyay. My till the 5 weeks, all the things are updated. So week 1,
Yeah,
week
sir.
2 till week 5, and you have the presentation folder as well in the middle where you can find the lecture notes or everything. And in my YouTube channel also, basically these videos are there, and in the description of all the videos also I am adding the reference to the notes and questions that I am
Sir,
discussing.
excuse me, sir.
Yes.
Sir.
In YouTube, what is the name of the channel, sir?
Okay, so
Sir, you just please share the link here. Means it will be available later, na? On like week 5 is available right now.
yeah, so I will
So
upload
week
it today
six
only, the week 6 by
today only.
tonight. By
Okay.
tonight, yeah, I do
Okay.
it usually that like that only.
Yeah,
I,
yeah, yeah.
I conclude my session in the night by 8:30 or 9 p.m. Then it takes some time to upload it. By tonight only, I usually upload it. I don't delay it. So if you
Okay.
check the Excel sheet which I just showed you in the NPTEL page, around
Yeah.
tomorrow early morning or tonight also after, let's say, 1 a.m. or so, you will find, or in my YouTube channel
Yeah.
also you will find that
Sir,
it's
tell me the
already.
name of the YouTube channel, sir.
Okay, so my YouTube channel is Avik Mukhopadhyay EE21D002. Okay, so Avik Mukhopadhyay EE21D002, but I mean that's not, you don't even need to note it down, because you already have this already links, the previous links, right? If you click the link, you will directly land up in my channel, right? So the links for the first 5 weeks, all the YouTube links are this. Okay, week 1, week 2, and so on till week 5. You just go to this sheet and just check out the videos, and you will know my channel. Okay, so yeah, I think we can maybe stop at this point. We've covered all the questions. Yeah, all right, so if there are no further queries or anything, we can maybe stop the recording.
Thank you, sir.
Okay, I will stop the recording.